proposition we're trying to prove, but I would like to talk about this special case. We're trying to show that 2 to the n is not a divisor of n factorial in general, of a natural number greater than or equal to 1. Let's work this special case to see if we can detect a pattern. Now notice right here that we have 1 power of 2 right here. So we have, this is 2 squared right here. And then notice that we have 2 times 3 right here, all right? So only 2 of the terms in 7 factorial, or 3 of the terms, have a factor of 2. Okay, so 2 times 3 right there. And of course there's a 2 right there, right? So this tells us straight up that 2 to the 4th divides 7 factorial. You guys familiar with this notation? This vertical bar means 2 to the 4th is a divisor of 7 factorial. Okay. Another way of saying that is 7 factorial divided by 2 to the 4th is a natural number. Okay. So anyway, now by the way, let's talk a little bit about how you might come up with this power of 4. It's easy to do with a small case, but this power of 4 was easy to count. 1 power of 4, 1 power of 2, 2 powers of 2, and then 1 power of 2, right? So that's where the 2 to the 4th came from, right? Okay, so how might that come about in some other way using some functions you might be familiar with? You could look at the floor function. That is the floor of 7 over 2. And you guys remember what the floor function does? It just returns the greatest natural number, the greatest integer that's less than or equal to the input. Okay, so this right here is the same thing as saying how many multiples of 2 are there in 7 factorial. Okay, and then this very next term here, let's try, we need 7 divided by 2 squared, I think. All right, and it's kind of clear why that's true once you go through the calculation here. Okay, now notice that this part right here is equal to 3, right? 7/2 the floor, 7/2 is 3 1/2. You chop off the fraction, you get 3. Now right here, 7 divided by 4 has a floor of 1, right? The greatest integer less than or equal to 7/4 is 1, right? So notice that the 3 plus the 1 equals to the 4 that you see right here that we just manually counted, right? It's easy to count this manually. Here's 1 2, here's 2 2s, and there's another 2, so that adds up to 4 2s, right? 4 occurrences of 2 functioning as a divisor of 7 factorial, all right? But this does the very same thing for you. The floor function does this for you without you having to explicitly expand out a larger factorial. Like if you were trying to do 23 factorial, this type of process would handle finding the highest power. Okay, now let's see what else to say about this. Notice that if you had 7 over 2 cubed, the floor of that would be 0, right? 7 over 2 cubed would be 7 over 8. I'll just write it out there. Plus 7 over 2 cubed. There's no reason to think you should do that, but that kind of gives you an idea how the process would terminate. Okay, notice that this would equal to 0 right here, right? And it wouldn't contribute. 7 over 8, the greatest integer less than 7 over 8 is 0, right? So this condition will always terminate. You just go through all the powers of the corresponding base that you're interested in. Okay, now, so what we've concluded right here is 2 to the 4th divides 7 factorial, but 2 to the 7th does not divide. Right? Okay, so something that looks like it's kind of natural is false. 2 to the 7th, I guess you might say that. 2 to the 7th is not a divisor of 7 factorial in this case. And what we're going to do is show in general that it's not the case. And so this will go pretty fast because we've already shown that the power of 2 in the prime factorization is given by this flooring process, and that's exactly what we're doing right here, except this is just a little more general. Okay, this is a little more general. Now let's go ahead and give this object a name here. We'll call it M. Okay, and all this is, folks, is just a generalization of the special case we just did above. So let's give it a name, let's call it M. Okay. Now, so down here, let's see, I'm off the screen here, but notice M is just all these floors n over 2, squared, n over 2 cubed ad infinitum, because we don't know how big n is necessarily. All right, so this guy right here is equal to M. So let me write this down. M is equal to this. We got to have something to call this. Okay, so we're calling it M. Now this next truth is very, very clear. The floor is always going to be less than the actual input argument, right? Just like right up here, the floor of 7/2, 3 is less than 7/2, right? The floor of 7/4, 1 is less than 7/4, right? So that's all we're doing right here. And it's really fairly simple. M is equal to this, but it's strictly less than removing the floor of those objects, of these three terms, right? Okay, and so what we get right here is that M, and y'all, I just recopy down here because I just didn't have room. But what we see right here is that M has to be less than N. And y'all, you see what I did? I did a little bit of algebra here. N over 2 plus N over 2 squared plus N over, oh, that should be 2 cubed right there, folks. Sorry. Yeah, this should be a 2 cubed right here. So let me get that. I just forgot to change that. So that's 2 cubed. Okay. And then this is also a typo on my part. That should be 2 cubed. All right. Sorry about that. Hopefully it doesn't screw things up. And I didn't even worry about it. I didn't go far enough out over here, right? Okay. But anyway, what I did is notice that you could factor out an N over 2, right? But notice what we get here. This is a well-known object here. This is called geometric series. And so this parenthetical quantity right here is just equal to 2. You guys remember 1 plus 1/2 plus 1/4 plus 1/8 and so on. Ad infinitum just adds up to 2. So you see that's how this all cancels out and you get M is less than N, right? So you see what we've shown is that M is strictly less than N, and that would mean that 2 raised to the M, okay? That would be 2 raised to the M would divide. That's the largest power of 2 that would divide. And y'all, sometimes they use this notation double vertical bars. So 2 to the M divides N factorial, all right? But that means, and again, folks, what this means, I think they say it just divides it. 2 to the M divides N factorial, but no higher power would divide N factorial, okay? So this implies that 2 to the N does not, y'all, and I'll put the negated relation here, does not divide N factorial. Okay, folks, and so that's QED time, because we've shown that M is strictly less than N, and 2 to the M is the power that would divide N factorial exactly, maybe is how they call it, but no higher power of M would do it. And so that means that 2 to the N does not. And that's what we were trying to show, right? Is that 2 to the N is not a divisor of N factorial, okay? Or that's exactly, that's another way of stating this. 2 to the N does not divide N factorial. All right, folks, let's see, anything else? I guess that's it, so we can put down QED here. Good night.